Okay, I'm Shachar Feinblit, the CTO. I will do the fun part, the technology. So I will start by explaining the main architectural trade-offs. I think this is the most interesting and most important element when building a storage array. And I will also cover what is the actual Kaminario product and with real deep dive to the details of what we are doing and how we are doing it, and also why we made these choices. I'm a real fan of the Tech Field Day. I'm sure that you will ask me many interesting questions, so please do it and we'll have fun.
Shar, you mentioned compression. Is it hardware compression or software?
Software.
Is it real time or is it post-process?
Real-time software. Okay, I will explain exactly how we're doing. It's software. It is byte-aligned compression, so we do not have any inefficiency in the compression and in the way that we are managing the data. So we are storing exactly the amount of data after compression without any internal fragmentation. And I will cover it. So I will start with the architecture mission. So Danny explained very well the company mission and our vision. And it is critical that the architecture will do it. And we believe that architecture is key because architecture brings a real differentiation. And a differentiation in the architecture means a real differentiation in the product. And we are focusing on differentiation to help customers scale their business easily and cost efficiently. It's not a secret that most vendors are using similar hardware elements. So similar SSDs, similar servers, and in order to be efficient, you need to get more from the same hardware.
I mean, you don't have 47 custom ASICs?
Not yet. Not yet. We are considering.
Not ever.
Danny speaks.
Yes. And what do I mean by lower overhead? Let's look at capacity performance graph. These are the main requirements for any customer. I need 100 terabyte, and these are my performance requirements. So if we look at the left side of the graph, it is a typical scale-up system. The system contains 2 nodes, 2 controllers, and it's possible to scale capacity by attaching more storage to the 2 nodes. But it is impossible to scale performance because you are limited by the performance of 2 nodes. Of course, you can buy more expensive controller, but 2 controller is the limit. If we look at competition, pure storage are using this approach. A different approach is scale out. Scale out is very good for performance and scalability. So when you are adding, you're scaling by adding more capacity together with more controllers. So a good scale-out system can scale performance linearly. The challenge of a typical scale-out system is cost. Normally, the density of such system is much lower than the density of a scale-up system. I mean the density of storage per controller. So these systems tend to be more expensive. And yes, you can get the best price per performance with a system that has many controllers and small amount of storage per controller. The best price per capacity is a system with the system that can scale out with high capacity attached to each node. And customer-specific requirement. So a customer needs some capacity requirement and a performance requirement. And if we look at this specific customer requirement as of the day of purchase, a single scale-up system, 2 nodes, 2 controllers, 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 is not able to meet the customer requirement. So in this case, such a customer will need to buy multiple system, manage multiple system, and when looking at data reduction, the data reduction will be less efficient because it will not be one global deduplication, for instance. A system that can scale out with low density per node. You can look at a few examples like Extreme IO and SolidFire, can meet the customer requirement. So with one system, you can meet the customer requirements of capacity and performance, but it is done by over-provisioning performance. Over-provisioning performance means to ask the customer to buy more nodes, which means more cost. So you meet the goal.
But don't the vendors address that, specifically in the case of SolidFire, by having multiple node types that they can mix heterogeneously with different CPU to flash ratios?
Okay, so it's all about the architecture. If you're assuming that all your metadata is in memory, you're limited on the density. If your RAID implementation is not very efficient, you will expose less capacity. And I can show that we can expose more than double the capacity compared to any scale-out architecture like Extreme IO or SolidFire.
Do you have an exact use case scenario where you work with customers and in another scenario they would have to scale out, but you found, hey, scale up might be a better approach here, and it allows you to differentiate yourself?
I tell you what we did. Danny was mentioning our Shield system. So when we see that customer is about to reach the capacity limit of the system, we are looking at the statistic of the system. And if we see that the customer is far from reaching the maximum performance of the system, we are telling him it's more economic for you to scale up. If the customer is getting close to the limits of the system, we tell him it's better to scale out. And this is part of the relations that we have with our customers.
That's why you get a lot of repeat business. Your Health Shield is giving them insight into whether a scale up or scale out is going to be the right solution for them, and that's great.
Yes.
But when you add a new node, so I understand. So for the scale up, you reorganize all the data inside the array. When you do scale out, you need to organize the data in a different, totally different way.
I have good slides about them, so it's a good question. So I know that some of you are very familiar with Kaminario, others are less familiar, so I think the best thing is to start by explaining what is a Kaminario system. So a Kaminario system is built from off-the-shelf hardware. It contains one or more building block, which we call a K-block. What is a K-block? A K-block contains two nodes, two Intel servers, connected InfiniBand back-to-back, and external connectivity that can be fiber channel or iSCSI. You can attach, the storage is not directly attached. We do not believe in direct attached storage because it's not efficient and it's very expensive to have an entry point system with direct attached storage, and I will explain it later why it's not efficient. We believe in shared storage, in SSD, shell full with SSDs, and if you want to scale up, you can add more SSD shelves.
How many?
It's today with certified 2. We are planning every year. In general, our rule of thumb is to double the scale up capability of the system, to double the density of the system. In this specific moment, we will first introduce more dense drive, the 2 terabyte drive. This is what we'll do this year. And of course, we will also add a third serve and support it. This is part of the architecture. The architecture supports multiple shelves. We believe that dense drive is more economical thing to do, and this is why we do first.
Consistent? I mean, is the cache coherent across the K nodes?
Of course. So we are the only also that can scale up and scale out. So you can start with basic entry point field system, It's very cost efficient. It's only contain a single K block, a single shelf, 2 nodes. We support multiple sizes of SSDs. Assuming that we see that customer needs more performance, we recommend the customer to scale out. What does it mean? Of course, everything is online, so there is no disruption to the operation of the customer. And as you see, before expanding the system, the volumes are spread across all SSDs and all nodes on the first K block. So every volume is, and the data and the metadata, it's very critical that both the data and the metadata are spread across all the SSDs. Now, when we scale the system, of course, we are adding an InfiniBand switch, actually 2 InfiniBand switch for availability, of course, and we are redistributing the data. So everything will continue to be fully balanced, both the data and the metadata. And this is very, very important. Why it's so important? Let's say that you have an Oracle application, and you can use a single volume and reach the maximum performance of the system. So we will not ask our customers to use multiple volumes or to change things. Whatever is the best fit for them of configuration of the software, of the storage, we will be able to deliver the performance without any tuning. So it is important for simplicity.
Okay. So
what happens to the front-end connectivity?
Sorry?
The front-end connectivity didn't scale out like the front end.
I think that's just the slide.
At the next slide.
Okay.
Oh my God.
Just
for your request.
So of course, the connectivity is fully active. You can access any volume from any node in the system.
And there's no Alua affinity?
No, not at all. Of course, it's fully active. We are using the multipass on the host. We don't need a special multipass because our performance is very consistent. So it's normally round robin or least queue depth. So it's not something.
How do you determine data placement? Is it
okay?
Okay, go ahead.
I have a more detailed explanation of the IO path that I will do later, but it's according to the hash functions that we are using, statistically distributing everything.
It's a content addressable backend.
No, it's not content address mapping. It's adaptive block size, and this is a real differentiation that we have, and I will explain it. Okay? We believe that content address mapping is not the right approach because you are just killing the CPU. You're doing too much processing, and with adaptive block size, you are much more efficient. I will explain it. Okay? It's
I'll have more questions when you get there.
It's a pattern that I'm really proud of, so I'd like to explain it.
Ah, yes, the proud papa.
Okay, of course, assuming that now your customer is very satisfied from performance, needs more capacity, customer will scale up by adding additional shelves, and of course, volume, data, and metadata will continue to be fully balanced across all resources, all SSDs, both shelf and each K block. So I think I cover all of these elements. So
there was
you had a great question about it.
There was a question from Twitter. Can you remove shells or K blocks while online?
Remove shelves while. So our infrastructure and architecture supported. What we qualified until now is to online expand. So, but we will of course edit because it's the same infrastructure to migrate data. So it's migrate in or migrate out. It's the very same thing.
Are heterogeneous generations of K nodes supported in the same cluster?
Yes, of course. We believe in.
Well, you say of course, but another company located in the same part of the world as you that was bought by those other guys that can't do that.
I will explain why it's so important. We are using all off-the-shelf hardware. So, and normally a system is still using for 5 years at least. Right now, it's not.
Their architecture says they should be able to do it too, but they can't.
And now we want to use our customer to use the most efficient hardware available.
Okay.
So we don't want them to continue using hardware from 2 years ago. It's less efficient.
Right. Well, that means that you have to get moving on
That's the difference between V5 and V2.
Right. But that means you have to get moving on the ability to eject a K node, because over the 6 years I've had it, I have 3 generations. The old ones I don't want anymore, and I got to do that easily.
I totally agree. This is why we first did the expansion and the mix and match.
Well, nobody's
and
going
we will be able to remove.
Nobody's going to want the eviction for a couple of years down
Yes.
the road. So it's okay that it came
This
later.
is why it's not our first priority thing to do, because it's not going to happen in the next few months.
You walk before you run. That's not a problem. It's
Yes,
just
exactly.
Yeah, you're right.
So, okay, the main challenge of any modern storage system is data reduction. In order to implement good data reduction, you need to have good metadata management, and data reduction introduces much more metadata. So you need to manage more metadata, and the way to implement data reduction, and especially deduplication, should be part of the architecture. And in general, there are 2 approaches for doing deduplication. One is called content address mapping. So it's very easy to understand it according to the name of content address mapping. 16K of data arrive to one of the controllers, and each architecture has its native block size. In this example, we are using 4K. We have vendors that are using 4K. I believe SolidFire is using 4K. I believe EMC Extreme IO moved to 8K because of the limitation that I'm about to explain.
okay.
And there are even someone is doing even 16K, but this is not common. So what's going on is that this architecture is splitting a 16K IO to 4 different IOs of 4K, and the address of each 4K is determined by the content. This is why it's called content address mapping. Okay, so in this specific example, we have 4 different 4K elements. Each one arrives to a different controller, assuming it's a unique write. So you need to dump each 4K separately. What does it mean? That it's less efficient. You got one IO of 16K, and you're doing tons of networking, CPU processing on each controller separately, more metadata footprint because you need a pointer for each 4K instead of one pointer.
But you get to distribute that load across all of the controllers instead of having a single pointer. You have to
yes, but what at the end result is that you are limited by the IOPS of the block size. This is, for instance, now you need to read it. You need to read like 16K. 16K is a nice example. I can use 64K. So you will do 16 different reads. Mm-hmm. Actually, if you are reading 64K, it's also problematic for the latency, because the latency is less consistent. Because if you are throwing 16 IOs of 4K, the latency of the read will be the latency of the worst case, okay, of all 16 reads. We believe it's not the right approach. SolidFire and Extreme IO are using this approach. We believe in an approach called adaptive block size.
Be with you in a second.
16K arrive to the system. If we do not gain any value from deduplication because it's a unique write, we are just storing the 16K continuously in one location. As you can see, much less processing done. Now, let's take an example of 32K.
I thought you said it got striped across all the drives. You're showing
So
it just landing in one place.
Our stripe is with a stripe size of 128K, and our block size can go down to 4K. So this is the best trade-off of performance. If you are striping everything to 4K, you are not gaining anything. You are just killing your CPUs.
I'm either misunderstanding or your diagram is showing something different than how you explained it earlier.
Okay, so
I'm misunderstanding.
if, for instance, if you get an IO of 512K, we will split it into 4 IOs of 128K, and each 120K will be treated like this example.
As long as it's less than 128K, it'll go to one of the K nodes to process.
Yes, and then when it arrives to the K node, then explain what is done. I have a very detailed explanation of the IO paths, so I will do it later.
You mentioned compression. I would have thought the 16K would have compressed too.
It's
Not showing compression.
It's not showing compression, but of course we are doing
Compression comes after.
compression
when
is real time.
when dumping the data to the drive, we are doing compression. I think I will show you the full IO path, and you will understand everything. Okay.
Okay, so as long as any one type of data is always being accessed by either large or small IOs, that should work fine. But using a finer grain should get me better data reduction.
No. This is all. This is the differentiation of what we are doing. So we will eliminate any 4K match in the system. But it's not that we are splitting everything to 4K. We are splitting only when we gain value. We are not splitting just to split. We are splitting only when we gain value of data reduction.
So if I do a 16K write,
yes,
you're going to calculate hashes on it on 4K boundaries and eliminate duplicates on 4K boundaries.
Yes.
But if it's 16K of unique data, you're going to do a 16K write.
Yes.
Okay.
Actually, more than this, because let's take the example of the 32K. Okay. So if it's unique, we will store the 32K in one location. But
we have to be very careful with the definition of the word unique, because because that 32K, if 31K 998 bytes of it are the same as some other 32K, by some definitions that would be unique. So saying unique at the 4K granularity.
Exactly.
Okay.
Exactly. This is very important for efficiency.
Yeah. Semantics are important. Yeah.
Yes, I agree. I agree, and good that you are telling me this. But let's take an example. Let's assume that the 32K, the first 16K equals to the previous write, and the new 16K and the other 16K is new. We will store locally only the 16K, but it's not that we will create 4 pointers to the other 16K. We'll have 1 pointer. Okay. We'll have 1 pointer. So it's even with data reduction, we are much more efficient in the metadata footprint. Okay. Okay. So it's very important. We are eliminating any 4K image global in the system. So it's not like architecture that moved to large block size like 8K, like what Extreme did. We are not doing it because we want to find a match on a 4K granularity. Okay. And we are breaking to the largest consecutive match found. Okay. So we are not breaking everything to 4K. If there is a value, we'll break it. Also break it in the most efficient way.
You've separated the I/O path from the dedupe granularity, which most people don't do.
Exactly, you got it. And in fact, the people that are doing adaptive block size, we are doing it, Pure are doing it, but we are the only vendor that implement adaptive block size in a scale-out architecture.
Well, it's a lot more complex to implement scale-out than doing the 4K CAS. Yeah.
Especially if it's a system which is active-passive, so it's not that difficult to do the adaptive block size. Yeah. Okay, when scaling out, this is the challenge, and it's not that others can do it because we have a patent. These are statistics from our airshield. The x-axis is time. I took it back in December, and the y is accumulative bandwidth. And what you see according to block size, blue is I/O smaller than 8K, green 8K to 64K, orange 64 to 256, and the red above 256.
Is that by count or by?
It's by bandwidth.
By bandwidth.
By bandwidth.
Okay, so the larger blocks are going to be
emphasized
compared to by count.
This is one installation or
No, it's the entire
across the complete
installation.
base?
Yes, because one install is not interesting. I think to look at the average of everybody is much more interesting because this is what customers are really doing.
But that less than 8K band is much smaller than
If
what.
it's a bandwidth level discussion, if you're doing 256K IO ops, you're doing a lot more bandwidth than you are doing with 8K IO.
Right, but
Not an IOPS perspective.
right, no, but even if you take that little blue band at the bottom and you say, okay, let's assume the average size is 64K, so those are underrepresented by a factor of 8. That still would move that blue band to like 30 or 40% of all IOs, as opposed to the 80% of all IOs in database applications we've been led to believe there is. So that's my point, is just when we test storage systems, we're using IOs much smaller than any of the data I've seen from any of these vendors in the past couple of years about what the IO size distribution really is.
But that doesn't that get us back to that discussion then, how that all of the discussion about block size is irrelevant because everybody keeps going on about half a K, 4K. You're sort of saying that that's not really that much of an issue. It's not all about how small a granularity you can actually support on your deduping.
Well, the dedupe and performance kind of unrelated.
I think what is important is the fact that we have adaptive block size. We are able to reach between 2 to 4 times higher performance on real IO sizes. So it's not the 4K benchmark that nobody cares, compared to other vendors that are using the very same hardware. So it's a real differentiation. So you gain more from the same hardware.
It's like a stacked bar chart. So I mean, effectively, the 64 to 256K is the biggest portion of the throughput, and the 8 to 64K is the second biggest, and the third biggest is 8K, and the fourth biggest or smallest is the 64 greater than 256K. It's a stacked bar, right?
So it's according to bandwidth. It's not according to IOPS.
Have you got that raw data with you?
Sorry?
Have you got that raw data with you? And could you divide it by the block size?
We want by IOPS.
Yeah, we'd love to see
Yeah.
Oh, okay.
So
We can take it off and I can show because we can do everything.
It'd be interesting to see. I think that's what you're saying. How divided by block size?
Okay.
See the number of IOPS.
Yeah, a percentage of IOPS at in each of these block size bands would be very useful data,
It's got to be finer
especially for
granularity.
those of us who test stuff.
Yeah.
Okay, let's move on. You want
Yeah.
You want me to show you the IO pass? You want me to show you the IO pass? So let's do it. So write only. So you see that the reads are slightly bigger than the read and write is slightly bigger than the write, but still majority of the bandwidth is much larger than 8K. We see that the average size that we see is 43K.
Okay.
We are not counting the X copy, which will just increase it. Okay. 35 to 40% is writes IO, so it's not the 80-20 that some vendors are referring to. 80% of the IO smaller than 8K is write IO. This is important. Why?
80%.
Because of the blue portion is small, but it's not neglectable. It's not neglectable, especially when you look at IOPS, as you said. And the thing is that if you are moving to 8K block size, it's not that you are only compromising on data reduction for deduplication, you are also compromising on performance because you will do read modify write, you will do decompress of large chunks when reading 4K, so you would need to decompress for 8K. So I think it's very important to know.
And writes are smaller than reads.
Yes, 90% of the bandwidth is with IO equal or larger than 8K, so still majority of the bandwidth is large IO. 70% of the read bandwidth is 64K and above. As I said, the reads are normally larger than the writes. This is what we see.
Yeah, now we need to,
Okay.
I need to see the workload mix because there's lots of applications that could generate very large sequential reads.
I agree. Backup.
Rich media.
Okay.
There are also many applications that prefetch a lot of blocks in
Yeah.
advance.
Exactly. If you're running full table scale.
Yeah, there's a lot of things that,
But
you know, we got to
it's
look.
not always the most efficient way to do full table scans, but customers are doing it.
Well, I mean, we have a lot of applications that are using memory as an internal buffer.
Yes.
Because they're assuming that the disk is so goddamn slow. And if that application was actually written for a 3 orders of magnitude performance difference between memory and storage, rather than 6 orders of magnitude, it would work differently.
So this pool of data comes from only V5 systems, coming from older systems, and about how many systems actually is it? I mean, sure, that's asking, hey, how many customers and deployments you have, but that's not what I'm curious of how large are the pool of this?
Hundreds of systems.
Hundreds of systems?
Yes.
Yes.
Okay.
Okay.
And is it across the workloads of V5 to V2, or is this all V5 only?
This is all V5.
Okay, perfect.
Okay. So what we also see that for the same range of blocks, we see different read and write sizes. So like ETL process loading data with large chunks and later running some real-time analytics with small chunks. So it's very critical to the way implementing compression, and I will cover it later. Scalability. So I think I covered that. We believe in a system that can scale up and scale out, not compromising on one of them, to be efficient and to be able to really scale performance and capacity.
Okay, so let me come back to the earlier question. How do you determine data placement? Because I've got 27 nodes. Yeah, I know you don't actually sell them that big yet, but I've got 27 nodes.
So
data comes in. How do you decide where to land it?
So we have a mapping table. It's a small table. We are using hash functions, actually CT hash.
Okay.
And
so this is separate.
So it is a table that is mapping between LU LBA to the node that is responsible to process this data. Okay. Of course, later on we are also doing the deduplication, so it's more complex than this, and I will explain it.
Okay.
But it is how it works.
But basically, you're assigning sections of the logical volumes to nodes.
Yes, with stripe size of 128K.
Okay.
Okay, we believe in system with it's a fully active. So we do not believe with leaving one server not working. It's not a way to utilize the investment of the customer. It's also not safe from high availability. If you are not using it, you cannot trust it on an event of failure. So we really believe in fully active everything.
Are you active 50% workload allocated, or active run them both to the max, and then if one were to fail?
We are not leaving 50% waiting. So we are leaving a small chunk. We also have some optimization, because when you have less failure, you have less networking to do. So this is how we can reach high performance on recovery without just leaving 50% off.
Just curious on that is, if a node fails, what's the impact? If a shelf fails, what's the impact, essentially?
Okay. When an SSD failed, I have slides.
No, the entire not an SSD. An SSD failed, fine.
And not a typical customer will not notice any performance impact, because he will notice an impact only when he's running on the full bandwidth. Mm-hmm. What we see is, and actually we are showing it to customer in demos, it's up to 20%, but this is very, very extreme. Normally it's nothing.
Okay, by node you're talking about a controller.
A controller, yes.
Okay. Because for your architecture, if I was talking about it in terms of scale out, a node would be 2 controllers and their attached storage.
Okay, this is called
and so
a
it's
block.
Semantics again.
Yeah, we call it a block, okay?
Right.
Okay, so this is the difference between a node and a block.
Okay, so is data protected against block failure?
A block failure?
Yeah.
Replication?
So data is protected, but the system goes down to secure the data. So the data is secure, you're not using any data. Of course, this is the architecture that everybody is using. Everybody is using shared storage. Of course, if the 2 nodes fails together with the shelf, this is the standard in the industry, and And we are like,
Perfectly good answer.
yes, it's not different than symmetric, HP.
Except that if I have 4 blocks, some of the data of every one of my volumes is stored on each one of those blocks. So a block failure means all of my data is going to be inaccessible. Where if I've got a clarion, well, if I've got 4 clarions, each one's an independent failure domain.
Okay, so we have failure domains on the RAID level, and we have a failure domain on the block layer. I will show it. Okay. Okay. A few more things. Scale out. Not all scale out architecture are equal. So we believe in a scale out architecture that spread data and metadata of every volume across all resources. And we believe, as you already asked, on a system that can mix and match. Global deduplication is, of course, a must for efficiency, and resiliency for multiple failures. So if you are pulling 2 SSDs on each shelf simultaneously, the system continues to run without any performance impact. If you can have a single node failure in every K block, and the system continue to operate.
So are the controllers rated across the shelves, and or are the volumes confined to a specific shelf? Like how is it rated or protected? If RAID is not the right word here, how is it protected across?
Okay, I have a slide about how RAID. Okay, so I think it's the best way to show it. I think this is the main challenge of a modern system: how to manage the metadata. Because with a system that supports data reduction and efficient data reduction that can find deduplication match of 4K, you need a pointer for each 4K of addressable data, and you need a signature for each 4K of unique data. Is it clear? Good. And it means tons of metadata. And we did few things in the architectures to reduce the metadata footprint. The first thing is our adaptive block size algorithm. Adaptive block size algorithm means that we have, for the same data, we have less pointers. Less pointers means less metadata, smaller metadata footprint. Regarding the duplication, people like this discussion whether to use strong cryptographic hash or weak hash and compare. So there is a debate whether strong hash, cryptographic hash is safe enough. I don't want to get into this discussion.
Oh, good, because we're more likely to get struck by an asteroid and killed than you're going to have a hash collision damage your data.
I agree.
Oh, let's not go over that one again.
Let's not spend, guys. Let's not spend time on this.
RPGs.
The real reason to use deduplication with weak hashes and compare is the metadata footprint. A strong cryptographic hash wins 256 bits. You can do it with quarter the amount of bits per signature and quarter the amount of metadata. This is very, very significant. So you can do, again, more with the same hardware. And comparing with SSD media means reads, and reads are cheap with SSD media. So it's a very, very, very good trade-off in our mind. Still, the metadata footprint is linear to the data reduction, because when the data reduction is high, you have more pointers. And the system density. So when you have more capacity, you have more unique data, so you have more signatures.
So
yes.
Sorry, is there a difference between data that's highly deduped, where it's the same data deduped many, many times, like VDI, or where you've got a lot of data that's only deduped a small amount of times?
So you
not care?
So we do not care, because the amount of signatures is related to the amount of data you have. Because you do not have unique data multiple times, you will dedupe it. So the amount of pointers is related to the data reduction. So if you are compressing better, if you are deduplicating more, you have more pointers. So if you assume that all your metadata is in memory, it means that you have a limit on the data reduction. And this is the secret that many vendors are not telling the customer. What is the limit of the data reduction when the system is full? I don't care what is the data reduction when the system is 20% because I don't need to buy more storage. I really care about the data reduction when the system is full. And the fact that we are using the capacity, the same capacity can be data and metadata, and we do not have hard limit regarding the amount of RAM in the system, then we can have a system that is full with like 12x data reduction, and it's NVIDIA environment, it's possible to be there. Yeah. We see customers that are filling the system with 12 data reduction. If we are comparing to competition, for instance, a full populate bricks from Extreme IO is limited to 6x data reduction. If you look at the spec from Pure Storage, it's between 3.5 to 4.5 maximum data reduction. So there are a few configurations, but one of them is 125 terabyte maximum. One is 250 terabyte maximum. So telling the customer, okay, this is our average data reduction, is not the real thing. Because will it be the same data reduction when the system will be full? This is the answer, the question to ask.
So is the entire signature table memory resident?
Sorry?
Is the entire signature table memory resident?
No.
Okay, so is the memory resident portion of the signature
yes.
table hit count weighted?
So we are caching the metadata both for the signature and for the data.
Right, but in a typical set of data stored on a deduplicated data store, there are some blocks that are duplicated thousands of times.
Of course.
And other blocks that are duplicated 6 times.
Exactly.
And so I want you to be weighting whether that table is stored in memory based on the hit count, so that the most likely data is in memory.
Exactly. So for instance, the data of the image of the Windows 7 will be in memory. Yes.
Okay.
Of course. And if you have a cache miss, it's SSD. It's not hard drive. You need to remember. So the impact is low,
which means it's only 3 orders of magnitude slower.
Yes, but the end result is that some vendor will say, okay, I have all the metadata in memory. I'm faster. It's not correct, because if you are doing content address mapping, you are killing the CPU, and you don't really care if you are doing some extra IO for metadata. The fact that we are doing adaptive block size together with the fact that we do not assume that all metadata is memory allows us to have better price points, better scale up capabilities. Our scale up capabilities are twice than all our competitors without compromising on performance. Actually, we have better performance per server compared to any other all-flash array.
Why?
Why?
Why are you better performance than... If you bring competitors up into it, what is it that you're doing that makes it better perform?
Okay, I can give you an example, adaptive block size. So if we can...
We got that. We got another example? I mean, because we saw you went through the whole spiel on the adaptive block size, so I feel like we've got that and how you're doing it. What's another way, unless that is the pure competitive differentiator between the alternatives?
I think the main differentiation is adaptive block size, and if you can saturate the fiber channel links, while others are about half or quarter of the bandwidth of the fiber channel links, it means that you are much faster. For instance, if a server can do 100K IOPS of 4K, so it means that your read bandwidth per server is 4K multiplied by 100K IOPS, which is only 400 megabytes per second. We can do per K block more than 3.2 gigabytes per second. Okay, so it's a real differentiation, and we are doing it without compromising on cost. Okay, because we do not assume that all metadata is in memory.
Sure, sounds good.
Okay, some statistics. I think you know all this stuff already. This really matters to our customers. 46% of the capacity we deliver was on system that utilized both scale up and scale out. these are systems with more than one K blocks, so it's 2 or more K blocks with more than one shelf per each K blocks. 52% of the expansion done were scale up. It means that around half of the expansion are scale up, the other half are scale out. Both are very important, so you cannot say that one is more important than the other. Density. 58% of the capacity we deliver was on system with multiple SSD shelves per K block. And some statistics about data reduction. So yes, on databases you see around 3.2x data reduction, but we have good portion of customers with data reduction higher than 7x. And we can fill the system with data reduction higher than 7x, which is a real differentiation in cost. So it's not that we are limited to 6x or 4x. We can fill the system even with, for instance, 11x, which are 14% of our customers.
A bit low on time.
I'm a bit low on time. Okay, I think I just want to say something about here. I think a few of you I saw in Twitter that really understand it. That direct attached storage cannot scale down compared to shared storage. Okay, and here I put some calculation of 87.5% RAID utilization compared to 4 nodes.
But you're speaking strictly in the theoretical here because you haven't told us how you do data protection.
Good question. Good question. But I just want to say that direct attach is not the right way.
Well, I don't think anyone in the room here was going to argue that DAS is exactly DAS, you know.
Yeah.
So because when we look at flash storage solution, we look at the entire marketplace of every flash storage vendor out there and the similarities between them. That's why we're trying to see the differentiators between them and how it correlates, because
exactly. But there are vendors that are using direct attached storage in their system, like SolidFire, XIV.
It makes a really good story when you talk about DAS or, hey, this is faster than your old Clarion. Yeah, my phone's faster than my old Clarion, so I get that.
Exactly.
So I mean, so that's why we want to get into the weeds around this.
Exactly.
Really.
So when we decide to do the data implement the RAID, we had 3 items in mind. One is cost efficiency. Cost efficiency, we were looking at 87.5% utilization. So not 50%, not 60%, high utilization. Resiliency, to sustain more than single thread, to sustain multiple simultaneous failures, so RAID with dual party, and to do it, the high utilization without compromising on performance under recovery and on good pass. So, of course, everything no rotating.
So it's
everything
2P plus Q?
It's 2P plus Q in a one stripe. And I will explain why we are doing it. This is for performance under recovery. This is the reason that we are doing it. Of course, when we are writing, we're always writing full stripe. So you do not have read, modify, write like in legacy.
Controllers have NVRAM for the log?
So our data is protected in RAM speed. We are using transaction-based algorithm. Today we have on each server we have a battery.
So there's NVRAM, fine.
Okay, but it's not NVRAM like SLC SSD or NVRAM or SSD. It's DRAM speed. It's important for low latency.
Is there anybody in the room who, when they say NVRAM, doesn't mean DRAM that gets backed up to flash or protected by a battery?
No, I think that the differential people there might be thinking is NVDIMM, isn't it, rather than NVRAM, I suppose.
Yeah.
No, but there are vendors that are saying that they have NVRAM and they are using SLC SSD or PCI.
And we know them, and they're in orange, and you can stop picking at them about not using industry standard terminology.
Okay. Sorry.
Is Q twice the size of P1 and P2 in order to accommodate the total parity? Or
No. So
that's what I'm maybe looking at it wrong. That's why I'm trying to understand how it
understand the Q.
So it's different mathematics. We are using a Razor code. It's half of the SSDs in the shelf. 5 of the SSDs is with party, like RAID 5, another half with P2, and the Q is protecting the entire shelf. Okay, so it's like a RAID 6 but protecting two RAID 5. This is what we are doing unique.
So it's
A queue is parity for the other two groups as if it were a single RAID 5?
Exactly.
Going to cover 2 failures?
Yes,
That's
exactly.
an interesting approach.
Going to cover?
Let me show. So
Overlaid. So it's overlaid RAID 5.
it's 2 RAID 5 and a queue, so it's a dual parity RAID, but is a RAID which is much more efficient.
right. Well, you
performance.
only need one queue instead of two.
Yes, and I don't have spare. I don't
Save
have
yourself a
spare
test.
capacity here.
Yeah.
And so what is the trick here? So if we have a failure, I'm doing a XOR of only half of the SSDs. This is also a differentiation that we have. So we are able to have very high utilization of 87.5, but on an SSD failure, we are doing XOR of only half of the SSDs. If we are comparing to a competition, for instance, so Extreme IO has similar utilization, but they compromise on performance under recovery because they build a regular RAID 6 with a full stripe of 1P and 1Q, so they will do a rebuild for all the SSDs in the shelf.
How can you not affect Q when you're updating this data in the first half of this? I don't understand.
No. So I'm always writing full stripe.
I understand you're writing
So
full
I'm
stripe,
calculating.
no problem.
When writing a
So at
stripe.
the time you do this, you're going to be creating Q at the same time. You're
Yes.
writing this P1 stripe.
But you're also
Also have
writing
to
the P2
incorporate
after.
the P2 stripe, right?
Exactly. So I'm writing data for 21 SSDs from the 24 SSDs in the shelf, and I have P and P1 and P2 and Q, which are calculated. Okay.
So, to the question I asked before, is Q twice the size of every SSD in there?
No.
No. It's
XORing over the top of the whole
Okay.
P1, P2.
So if P1 if the first block is 5 plus 1 RAID 5,
Yeah.
then you do XOR of 5 and you generate 1.
Yeah.
To generate Q, you do XOR of all 10, but it's still the same size.
Gotcha. Okay.
okay. Now,
Not to say that you're necessarily doing XOR, but it's easy to explain that way.
okay, exactly. So we have a failure. So what we are doing, this is to answer your question. We are merging the two P1 and P2 into a single P. So we are transitioning from a K RAID to RAID 6. Okay, after a failure.
So it is made single P.
Basis?
We are doing it stripe by stripe basis. So it's not that we have an hotspot of one SSD. Every SSD has some Qs, some Ps, and most of it is data.
So it's
Can you sustain 2 dropouts in the first half stripe there?
Yes, I can often explain you the mathematics of how we are doing it, but of
Maybe
course.
later. Over a beer.
Now we understand complex erasure codes with bourbon better.
So one question: this single P means it's recalculated, or it's only the P2? Parity is
The second P, actually, I'm merging the two. There is a very easy way to merge two Ps into one. Okay.
It's
Better performance under recovery. Actually, we show it in demos that there is no impact noticed on when an SSD fails. And of course, you can have a second failure. When you have a second failure, then we are doing a recovery similar to a regular RAID 6, and we're transitioning from RAID 6 into RAID 5. Of course, when things are recovered, we can return. We are returning back to K-RAID. Something to mention: yes, we can sustain 2 simultaneous failures. You can just pull 2 SSDs simultaneously, and the system will sustain it. We are doing demos of this. In general, 2 SSD failure is not very common, but something that we see that sometimes happens, you can have a full SSD failure and some sector error of one of the other SSDs. So it's like 2 simultaneous failure for specific stripe.
So the array will randomly change between RAID 6 and RAID 5 based upon failures,
Yes.
essentially?
Of course, if it's
Not randomly, I mean.
it's not randomly, but and I want to mention that of course, if it's one sector fails, so we will do a recovery only for the stripe. We'll not do it for the entire SSD.
Sure.
But if the SSD failed, we will.
SSD fails or we pull one out for whatever reason,
Yes.
we'll
do a full
accommodate
recovery.
based upon its workload and such.
Sorry.
It's all good.
Okay.
So this P1, P2, and Q will be available in every shelf, or it will be across the entire system?
So we have failure domain each shelf, and we implement a software RAID for each shelf independently. So if you have a system with, for instance, 2 shelves, you can pull 2 SSDs in each shelf, like pulling 4 SSDs simultaneously.
Okay,
No
we
problem.
can define that.
Sorry?
We can define that, or
It's what we support now is a RAID per shelf. Okay, this is what we are doing. Of course, with the infrastructure, we can do other things, but this is what we do now because we believe in fault isolation. Okay, so regarding data reduction, I do it very quick. I spend a global and adaptive. One more thing that we are doing, our deduplication is selective, so you can.
That explains how you got SPC1 results. 'Cause they won't audit if you have.
Actually for SPC1 result, you need to turn off dedupe and compression because it's not allowed. So we didn't run it with data reduction. Okay. By the way, we ran it in the lab. We improved things since then, but it's not something official that we can publish. Okay.
Yeah.
And this is a significant differentiation in databases. Because performing all the deduplication processing without getting any benefits is just waste of CPU resources and waste of DRAM. We don't want to waste these resources for nothing. And I think I also already covered everything about compression. These are average data reduction. You were asking, guys, you were asking about some statistics. So average is 5.9, also for a full system, not just for a system that is 20 or 40% full.
What's the x-axis?
It's time. I think it's I'm not sure that I put it, but I think I took it back in December, like the other slide. This is probably the time.
When you say a full system, what does full mean to you?
Using
the 80%, we're talking 100% fully max.
Normally, customer, I think they can feel safe with 90% system full. I don't want our customer to run like 98% full because
that's fair.
Yeah,
because that would be stupid.
Yes, exactly. Okay, some statistic you were asking about. So in database with the 3.2x data reduction, 96% of it is compression. Deduplication is an overhead there. Right. You don't want to do, and this is why our customers are disabling deduplication on database environments. Server virtualization with 5.5x when 60% of it is dedupe, and VDI, of course, you get 9x. It's 9x when really using the desktop. After cloning, you can see 60x, but who cares? Yeah.
What's like the percentage of usable capacity to raw capacity? Thank you, Jay Metz. So like, what would that be?
Usable to raw?
Yeah, the total percentage of usable capacity to whatever the raw capacity in the box is.
Okay. So if it will be, we said 5.9, so it will be on average about 4.6. I'm just calculating now by adding some like RAID overhead and some over provisioning. Okay. Mm-hmm. This is a nice picture I really like. It is a 4K block system, 2 shelves in each K block, and we pull 2 SSDs in each shelf, and we shut down 1 server in each K block. So it's 4 servers down, 16 SSDs out, and the system is in full operation. Okay, this really demonstrates our fault isolation. Regarding, I think Danny already covered that everything is online, capacity, scale up, scale out, hardware replacement, and non-disruptive software upgrade and firmware upgrade for anything, including SSDs. Because you have firmware and SSDs as well.
Are you saying anything about the SSDs themselves?
The exact vendor that
Well, if you want to give me a model number, I wouldn't object. But
Okay.
are you using
I will be nice.
MLC, EMLC? Are they are they off the shelf SSDs?
Okay. I think you will be able to guess. We are using 3D MLC. Okay. Okay, and we can discuss it offline if you want.
Don't need to. I know.
Okay. I knew that. Okay. Snapshots. Our snapshots are space efficient, both for the data and the metadata. When you have deduplication, you can say, okay, I can just, for doing snapshots, and this is what some other vendors are doing, I can just replicate the metadata and take advantage of the deduplication to not duplicate the data. We believe it's not the right approach. We implement a native snapshot implementation where the data and the metadata is space efficient with thin provisioning of our native small block size of 4K. So our allocation unit is 4K. So it's very efficient. And taking a snapshot, and we'll see it, I believe, in the demo, is like an IO operation. So you will not notice any performance impact when taking a snapshot. So it's very different than what people think it's snapshot is. It's really a new way of doing snapshots, and the performance of a volume after taking few snapshots, and the performance of a snapshot, a writable snapshot, is the same. There's no impact on performance when taking a snapshot. This is, by the way, in addition to the data reduction. Actually, an interesting story is that sometimes with databases, we see customers with ID to ratio, and we ask us, what's going on? And we realize that these are customers that are used to just replicating the data instead of using snapshots, because they are used to use legacy storage where snapshots are not that efficient like we do. So when we see it in our AirShield, we normally tell our customers to start using snapshots instead of just duplicating data and duplicating the same data multiple times, which is very inefficient. IO pass. How much time do I have? I'm okay. Okay, so I think this is the most important part of my presentation because it really explains how we do things. So let's start with unique write. It's a 16K write. According to the multipass, it is arriving to one of the nodes. In this case, it's node number 2. We are performing a lookup in a table. We call it a mapping table, that it is mapping between LU, LBA to node ID. The stripe is 128K, as I said. So in this case, it's node number 3. We have 2 copies. The copies in memory, it's memory speed copies. It's a real well-defined environment, and so we can return acknowledge back to the host. And this is the easy part, of course. Now it's becoming more interesting. So we have 2 copies protected, and we need to check whether we already have this content somewhere globally in the cluster. So we are performing a lookup in a table, a distributed table called the dedup database. It's a table that can go down to granularity of 4K, as we discussed. Of course, each node is responsible for portion of the hash results. So here we have, in this example, 4 nodes. So each node is responsible to quarter of the hash results.
So to echo on a question Ray asked about now, so where is that table stored? Is it stored in memory? Is it shared across each of them? Right?
It's, as I said, it is stored on the actual SSDs, and we have caching of this table in memory. But we do not assume that entire table resides in memory, because we do not want to limit the scale-up capability of
So
the
is it spread across portions of one or many SSDs? Like if you were to say, hey, my database, this dedupe database is stored here. If you were to like go point on the screen and say, it is here, so you could say it's in all of these boxes and in a partial, and then the rest else?
So the metadata is protected using the same rate that I explained. So when we are protecting a metadata area,
it essentially has a invisible volume it's accessing, like how NetApp does they write their stuff to the aggregates.
Yes, exactly. It's invisible. So it's internal. We do not want to add any complexity to the customer. Exactly.
Sure. We just want to make sure that if the wrong thing fails, that we don't lose that table.
Of course not. It is well protected.
And it's sharded across the various nodes?
Yes, so in this case, you have 4 nodes, so each node is responsible to quarter of the hash results.
Of the hash space.
Hash space, yes.
Okay.
In this case, we are doing a lookup, and we see that the 16K is unique. Any of the 4K within the 16K does not reside anywhere in the cluster. So we are updating the dedupe, distributed dedupe database, and we need to protect the data on the RAID. So we are using log structure array approach. We believe that using log structure array approach in our layer is better than doing it on the SSD layer because it's
they'll
optimized.
Do it anyway. You can't stop them.
Yes, but the question is how much over provisioning you put there, okay? Because the question is where you spend the over provisioning. Are you spending it on the SSD layer or you are spending it on the storage system layer? We believe in doing it on the storage system layer. And why? Because this allows us to implementing byte-aligned compression. Okay, so our compression is very efficient. We do not have any internal fragmentation in our compression implementation. So in this case, you see, as I mentioned, you have 4 elements of 4K. So the first one was compressed to 2K, the second to 123 bytes, and so on. We are compressing each 4K separately. This is because if later, after writing 16K, if the application is reading 4K or 8K, we will not need to decompress the entire 16K. So this is why we are compressing each 4K.
So each 4K has its own dictionary?
Yes.
Okay.
Okay, so actually for the 16K, we have one pointer, actually a pointer and all the offsets of each 4K, and we dump it to the RAID. And we are dumping when we have a full RAID stripe to dump. So we don't have any read modify write. And when the data and the metadata is protected, we can get rid of the NVRAM copy on both nodes, and we are done. So a few things about the table. So I already covered the mapping table, mapping between LU, LBA, and the node that is responsible to process the data. We have the same table on every node, and it's a very small table. It's like 64K entries, that's all. You don't need more than this for...
Do you have data integrity metadata as well? T10 diff or...
So we do not support T10 diff from the application, but we are protecting the data. So the data on the SSD is with signature, so we are verifying that the data is safe.
Okay. So you are doing block signatures?
The dedupe database, so it's across all the nodes. Each block is responsible for a portion of the hash results. And address table is the mapping between the LUABL to the location on the RAID when it's a unique I/O. When it's a dedupe hit, and I will explain it shortly, it will be a pointer to a different location in the system where the data resides. And let me explain it. Okay, the first part is what I explained previously. So it's the early acknowledge. So in this case, the multipass, we arrive to node number 1 and to node number 4, and we got an acknowledge. Now it's the interesting part.
So I mean, if the I/O comes in this case to like node number 3, with that 16K block comes into node number 3, and it's really supposed to be on node number 1 and node number 4, you're going to write that data into those two memory systems? Is that, I mean...
No. So the node that received the first write is the first copy.
Is always the first copy.
Yeah, and according to the mapping table, we are going to put the second copy there.
There's no ownership, Ray, is there?
He is the one that's responsible to perform all the data reduction optimization later on. But when you already have one copy in one node, you don't need to copy to 2 more nodes. So just another node is enough.
So you update the mapping of which blocks are on which node based upon where they first land. Is that
yes
how it works?
No. So
there's really no fixed mapping of
no,
blocks
it's according to the
nodes.
mapping table.
It's all variable.
Let me explain it. So it arrived to node number 1.
Let's say you wrote to node number 3.
So data comes into an arbitrary node.
Yes.
There's a table that says that some other node is responsible for
this portion.
That LUN LBA combination, so logical address.
I understand that.
And then it gets copied. But what happens if the data comes into node 4 and node 4 owns that portion of the space?
So it's you have much less only you don't have the extra op, and you are protecting. You are choosing additional node to protect the data. So you need to
so that node randomly picks somebody else to hold the safety copy while he figures out what
exactly
to do.
Because you cannot have 2 copies on the same node, of course.
Okay. Now, are there multiple logs being constructed? One owned by each node?
Multiple logs? What do you mean?
Well, multiple blocks of data are incoming, and they're being accumulated in the log into full stripes. But it's a distributed process, so does each node accumulate a stripe for its section?
Yes. Okay. Yes. Okay. Because otherwise, you don't want to coordinate stripe between multiple nodes. You don't want to do it. So it will be huge overhead.
So the data is replicated across blocks and then rated within a block?
It's replicated across nodes.
Blocks, nodes, okay.
Okay.
Nodes?
Nodes.
Oh, it's a distinction between a node and a block here.
A block is 2 nodes.
What other people would call controllers.
So you
Thank you, Dave.
a block is highly available, so it will be...
Block is what someone else would call a node. A node is what other vendors call controllers.
Anyway, when you have 2 copies in 2 different controllers, in 2 different servers that are fully separate, then it is safe to retain and acknowledge. Okay?
And if there's just 2 nodes, then it would randomly select the other node, right?
The processing is very difficult, but
randomly select from 2 or 2.
Now, from a response time perspective of what's going on as it performs each of these activities, 1, 2, 3, 4, are we talking microseconds, milliseconds? What's our actual
So we are using InfiniBand network, so one hop in our architecture, including all the software stack, is around 50 micros, so it's not that much.
Gotcha.
Okay.
And you expect the data to be, data is being split across all the blocks / nodes. So the size of the capacity of each node is growing at pretty much the same level?
Exactly, because the mapping table is redistributing the data across all nodes in a very balanced way. Okay.
Even regardless of the fact that the block could come into the wrong node?
Of course.
Yeah.
This is why we are doing it. Otherwise, if we were picking always the same node, it will be unbalanced. It's not good to do it. Okay. So we are looking at the 16K. We are performing a lookup in the Dedup database, and we see, yes, we have this signature in the Dedup database. But now remember, we are using a weak hash. We are not using cryptographic hash. So we need to compare the data. The good thing about it is because we are using adaptive block size, it will be 1 IO operation to compare the entire 16K of the IO that I wrote previously. So it's very efficient. And we understand that node 3 contains the data. So we are updating the metadata. We are also updating the reference count of the block in node number 3 when the the metadata updates are secured. We know that they are secure in the RAID. We can get rid of the do copies in the right buffer, and we are done. Of course, a read will come to one of the node. We perform a lookup in the mapping table. This example you were asking, it can be on the same node, for instance, and you have probability. I think it's the fourth time we are using this table, so statistic works. And we understand that the data resides in node number 3. So we need to read the data. We are reading the data while performing one IO operation for the entire 16K. And remember, we already compressed the data, so now we need to decompress the data. So we are decompressing the data and returning the 16K back to the host. Very efficient. So it's one IO to the disk, as opposed to content address mapping that in this case was supposed to do 4 IOs to the SSDs and with much more metadata footprint. I think it's your turn. Just before, do you have more questions?
I think we either got it or, well, Enrico has a question.
Just one question about the topology of the cluster. So you have the InfiniBand switch.
Yes.
How many ports are available for expansion?
Okay, so we are using, actually we have few models of switches that we are supporting. So I think we are using 8 or 12. I believe 8 ports per switch, and you have 2 switches for availability.
So 8 port means
it's
4K blocks.
So it's 8K blocks because you have 2 switches. Okay.
Okay, 8, yeah.
That's the current maximum you can go right now, 8K blocks.
The thing is that we believe in scale that is cost efficient. I believe that you got it. We see that our customers that are reaching a system with 3-4K blocks are normally scaling up because they are very, very satisfied with the performance and they don't want to overpay. So you can say the system is designed also for 20, 30, 40 nodes. We didn't design a system for 200 nodes. It's not what we did, but for 20, 30, it is well architected and designed. But we see that the sweet spot is between 2 to 4 K blocks. Okay.
Let me try a different version of the question. What is the current maximum number of K blocks that can be put together in a single system?
So we support today, and we have a system in the field that are running with 8 nodes, 4 K blocks, support out to 8 K blocks.
Okay.
We believe it's more than enough for enterprise customers.
I was just looking for a number, that's all, just to make sure I understand.
Yes, it's a fair question.